So let's talk about this required practical investigating springs. So what do you do in this practical? Well, you are going to be given a spring and you are going to determine the spring constant of that spring, which, if you remember from a previous video, is like a measure of the spring's stiffness. Oops. And to do this, we're going to need to use an equation. F equals, no, we solved this equation last video, but I'll go through it again. F equals K times E. Force is the spring constant times extension. Now the units for these are quite important, so I'll add them just now. The force is in newtons, the spring constant is in newtons per metre, and the extension is in metres. Okay, let's dive into the actual method then. So step one, you are going to need to set up some equipment. You are going to get a clamp stand, something like that. Equipment. Okay, and then you're going to hang a spring on it. And you're going to need something for measuring length, so you're going to need a ruler. And let's say that let's determine the unextended length of the spring. So the top of the spring, let's say, is at 1 centimetre, and the bottom of the spring, let's say, is at 5 centimetres. So let's say that the unextended length of the spring is 4 centimetres. Now, why is that important? Well, because if you remember the equation, we need to know the extension of the spring, not its length. We need to know how much longer it's got. Now, it can sometimes be a bit difficult to measure the length of the spring. So what you might want to do is add some sort of pointer or marker to it. I've seen it done with a pin. I've seen it done with a match. I've seen it done with an actual, cut out piece of paper, an arrow. So there are lots of different ways to do it, but it helps to improve the precision of your results so that you are always measuring from one point and you're not sort of varying the point you measure from. Okie dokes. So what do you do now? Well, you are going to want to hang a mass on it. So step 3, hang a mass. And let's say, for the sake of example, this has a mass of 100 grams. I've just lost it off the bottom. 100 grams. Perfect. Now this, even before we hang it, is a problem, because if you remember what we're doing, we're looking at force, and force is measured in newtons. 100 grams is not a weight, it is a mass. So we need to convert that into a weight force. How do we do that? With our old friend W equals M times G. So we don't know W, we're trying to find out what the weight force is. The mass, now we've got to be a little bit careful here because this number needs to be in kilograms, so we need to divide by 1,000. So that's 0.1 kg. 0.1 kg times by the gravitational field strength on Earth, 9.8 newtons per kilogram. Okie dokes. So what does that come out as? What's the weight force? Oh, I will need my trusty calculator. Where's that gone? Right, there it is, right. So 0.1 times 9.8, 0.98. The weight force is 0.98 newtons. And you see, the thing is, when you come to do your results table, like so, it's important to know that your force is 0.98 newtons. Okie dokes. You then backtrack and then you hang your mass on your spring, and it. So what did we say? We said it started off at 5 here, and then let's say that you hang it on and it extends and does that, and you measure it there and it's 9 centimeters, right? So that is an extension of 4 centimeters. Problem though, I can't just go and write 4 into this table because the extension has to be in meters. So what I have to do is I have to convert 4 centimeters into meters by dividing by 100. Where's my calculator gone? 4 divided by 100, 0.04. 0.04 meters. 0.04 meters. Perfect. You then might choose to add another mass to it. This will increase the weight force, obviously. So you stick another one on. So let's say that that's another 100 grams. Now the nice thing here, I don't know if you remember back to a previous video, but I said that weight and mass were directly proportional. You double one and then you double the other. Well, I've just doubled the mass. So 0.98 times 2, see the sneaky quick way of doing it, 1.96. So with two of these 100 gram masses, it is 1.96 newtons. Okay, so you then put it on your spring and it extends like so. And then let's say that that has come in at 13 centimeters. So we're talking about another extension of 4 centimeters. So the extension now is the 4 plus the 4, because overall it has extended 2 lots of 4. It's extended by 8 centimeters. 8 centimeters divided by 100. 0.0 8 divided by 100, 0.08. 0.08 meters. And you can continue adding more and more masses, therefore increasing the force on the spring and making it go longer and longer and longer. So eventually you will reach a point where you are ready to draw a graph. So here are some axes that I prepared earlier. And what we're going to do is we're going to have the extension. So that's blue for extension. Extension, remember, in meters along the bottom. And then let's say that what was force? Force was yellow. There we go. Force in newtons up the side. And you start plotting your data, and you will notice that your graph goes through the origin. Why does it go through the origin? Well, with no force on the spring, it obviously will not extend. Your graph will be a nice straight line until it starts to curve off like that. Well, what's going on there? Well, that means that with a little bit more force, you're getting a lot more extension. Basically, what you have done is you have busted your spring by going past the limit of proportionality. Do you know what? I can't spell. Let's try that again. Proportionality. Perfect. Yeah, the spring is not coming back once you've gone past that point. Now, we're only going to be interested in the bit where the gradient is constant because we need to work out this spring constant. If you remember, we are trying to work, we've got F equals K times E, and what we want is we want K. Quick triangle. There we go. So I need K and E next to each other on the bottom because they're multiplied together just there, and I need F on the top. I want to work out K, F divided by E. So K equals F divided by E. So I'm going to need to divide force by extension. I am going to need to work out the gradient of this graph. So what I am going to do is I'm going to turn the straight bit of my graph into a right angle triangle. Like so. So I'm going to avoid the bit where the line starts to curve and just use the straight bit. And I am going to bring a line down like that. Perfect. Now it's a triangle. So what extension has this undergone? So starts at 0 there, and let's say that this line of the triangle comes down, and the value it hits at is 0.0167 meters. Okay, I'm going to need that number later. And then we draw a line across from the top of the triangle to meet the y-axis, just like that. And let's say that it comes in at 5. Okay, so what we've got here on our extension axis, on the x-axis, is that we have a change in extension. The change in the x-axis is 0.0167 meters, and the change in the y-axis is 5 newtons. Now to work out a gradient is change in y divided by change in x. So what we've got is we've got 5 newtons divided by 0.0167 meters. Perfect. Let's punch those into the calculator and see what we get. 5 divided by 0.0167 comes out as being 299 point lots of numbers. I'll just go to the nearest integer. So that means that my gradient here is 299. But it's more than the gradient. That's the spring constant, you see. That was the stiffness of the spring that we were looking at back at the start. So this is 299 newtons per meter. This is a measurement of our imaginary spring's stiffness. Okay, so let's just go back to our method. You hang mass, work out extension, repeat with increasing mass. 6, draw a graph. And step 7, determine the gradient. Because the gradient of that graph, that is your spring constant. And that is what we were looking for all along. Thank you very much.